Hello. So the project's name is Path Planning and Obstacle Avoidance using Rapidly Random Exploring T stereo camera and OpenCV. So what the algorithm that I used to pan my path was RRT, or Rapidly Exploring Random Trees. It is designed for efficiently searching non-convex higher dimensional spaces, and it is constructed incrementally in a way that quickly reduces the expected distance of a randomly chosen point to the tree. So in layman's term, what the algorithm does is once you give it a start and an end point, it randomly generates sample across the entire map and ties each sample from the start to its nearest sample and creates a node, and it maps the Euclidean distance, and then it does it incrementally until it reaches the goal point. And after that, I introduced a bias function to get more randomness and a cost function to measure the entire Euclidean distance of my path and give me the optimal path that is needed for obstacle avoidance and path planning. So for what I did for this was I first created some images I created a stereo camera setup at first, which consisted of my webcam and my mobile device. So both the devices were placed approximately 28 centimeters away from each other. So I tried to mimic a stereo cam, but the problem here was that the focal length of both my camera modules are different. So whatever I do, I won't get the right parameters. So this is just a prototype of what is possible by the use of stereo camera. So for that, I calibrated both the cameras. So here's my calibration file. I use the OpenCV's camera calibration to get camera matrix for both, and then I use the get optimal new camera matrix to get new camera matrix in order to be able to rectify and distort it. And so OpenCV has a function called rectify unit rectify and distort. With the help of unit rectify and distort, I was able to generate stereo maps for both the cameras for X and Y. Here it's in an undistorted rectify map. So it created both the stereo map for both my cameras for X and Y coordinate. And I saved this in the stereo map XML, as you can see over here. But these are not the right digits because both the camera have very different focal length and very different setup. The image width is for one is across 640 pixel and for another it's across 1080 more than 1080 pixels. So it would have mapped the it would have estimated the depth extremely accurately, but I didn't use it because it would have given me even worse result without having a proper stereo camera. So after that, I did the object detection. So the object detection as a function called shape recognition. So what I did was find contours and then get the area, the perimeter, and the approximate polydp. So and the length of the approximate polydp would have given me what kind of shape it is. So I wanted a blue rectangle to be detected as my object. So I made it in such way, and I also got the center coordinates and the position coordinate for the rectangle, the obstacles that I was detecting. It were saved in a yeah. So I used the distance camera to generate a function to get my angle of view from the camera, from my mobile camera per se. I would have gotten it for both if the focal length was same. So using the camera metrics, I got the focal length for X, focal length for Y, and by using this formula, I got the angle of view, which was needed for depth estimation. So I had all the parameters, so I created another Python file to find my depth. So the way it works is by triangulation. I gave it the baseline, the distance between my cameras, the angle of view of my camera, the width of each image from both of my cameras, and the focal length of my camera. So what it does, it detects the object and it gets the pixel information in one camera. It takes the pixel information from another camera and it calculates the disparity, which is the displacement between both left and right frames. And by using this formula for triangulation, I calculate the approximate depth of the object from both of my cameras. So let's start the obstacle detection program. and it should generate my mask for both. Okay. So as you can see, it's detecting the red obstacle over here. This is just a prototype. I had the entire obstacle track mapped in my apartment. So, and you can see that it's showing the distance and when it loses tracking. So it's approximately 100 centimeters from here. This is mostly due to trial and error. It would have been perfect if it was a stereo camera setup. So the distance, as you can see, it's decreasing, then it's increasing. Okay. Okay, so let's move on to the RRT algorithm. So for the RRT algorithm, I have to create an RRT map and an RRT graph. Just so the map is just to draw the path and the obstacle, and the graph is where I declared my functions to generate obstacles from the extracted pixels from my object detection. And it makes obstacles, it adds nodes, it adds edges, it calculates the distance, it generates random samples, and if then it sees if the obstacle is free or not. I use Pygame for this, and then it sees if it crosses an obstacle. If it crosses or collides with an obstacle, it will either change its path, and if I'm generating some random obstacles, then it will not generate the random obstacle over there if my random samples are colliding. Or it won't generate the random samples if there is already an existing obstacle over there. So none of my random samples will go either into the start or in the goal pixel range or in the obstacle pixel range. And here's my main file for the RRT. So we just took that red obstacle and we mapped its coordinate in an CSV file. So the position.csv. So the position.csv is read into my main file, and now, as you can see, it will generate the obstacle path. You can see the red line over here is the optimal path for it to go from start to end. And here it only generated the one obstacle, as you can see in the gray, which is approximately 78 centimeters or 78 to 100 centimeters, and it's converted into the pixel, and it's just going through the path and it's going over there. Right now the cost function is not optimal. That's why you can see that it's going around a bit. If I had implemented my cost function, it would have been a straight path over here. So let's see, I just committed this and uncommented my previous obstacle path. So let's just run this and let's see. So it mapped all the obstacles you can see, and it found the optimal path from my start position to my goal position. And I had to move this camera a bit, the camera setup a bit in order to be able to map obstacles which are like directly behind each other. So that's how I got the obstacle mapping over here. I also made a traffic sign detector CNN, which I'm going to implement this later. So what it will do is it will take the obstacle, the rectangle that I detected, and it will have some kind of traffic sign over it. It will pass it to the convolutional neural network model, and it will give me uh, the directions where to go. Like if there's a speed limit of 50, it will pop up that it will show, oh, it's a speed limit of 50. If it's a pedestrian crossing, it should slow down. If it's a stop sign, the obstacle will stop. If it's a right turn only, the RRT path planning won't go to the left, and it will just consider the nodes to its right. So it's still in progress, but due to limited time, I had to do this right now. So that's what's my project. Thank you.